captivating world of Jupiter, the true colossus of the solar system. That gas giant has fascinated humans for thousands of years, and its sheer size, fast rotation, and intense magnetic field set it apart from all the other planets. Atmosphere driven by powerful winds, including the iconic cloud stripes and the legendary Great Red Spot. We'll also visit the remarkable Galilean moons, Io, Europa, Ganymede, and Callisto, each a world of its own. Join us as we retrace the path of historic space missions, from Pioneer to the groundbreaking Juno probe, uncovering the marvels of the Jovian system. So sit back and enjoy the show. Jupiter, the most massive planet in the solar system, known to humanity since prehistoric times. It is the third brightest object in the night sky, after the Moon and Venus, and can be observed with the naked eye, even in twilight, when the Sun is low on the horizon. Jupiter is the fifth planet from the Sun and has a mass more than twice that of all the other planets combined. Its diameter is approximately 140,000 kilometers, equivalent to about 11 Earth diameters. Jupiter is 318 times more massive than our planet, and its volume could fit over 1,000 planets the size of Earth. Located at an average distance of 778 million kilometers from the Sun, or 5.2 astronomical units, it follows an elliptical orbit, slightly inclined to the ecliptic, with an orbital period of nearly 12 years. Jupiter is the fastest rotating planet in our system, completing one revolution in about 10 hours. Its axial tilt is only 3 degrees, so seasonal variations throughout the year are negligible. Due to the lack of a solid surface and the centrifugal forces created by its rapid rotation, Jupiter's equatorial diameter is more than 9,000 kilometers larger than its polar diameter. Along with Saturn, Jupiter is a gas giant. The chemical composition of gas giants is very similar to that of the Sun, consisting primarily of hydrogen and helium. Jupiter formed in the early stages of the solar system, when the protoplanetary disk around our star was dense and rich in light elements. According to one of the leading hypotheses, the planet formed as a rocky core, which through gravitational accretion, amassed vast amounts of gas. The core itself resulted from multiple collisions and mergers of many smaller bodies and was about the size of Earth. However, there is no clear evidence that Jupiter still has a rocky core. If it had one in the past, the core likely eroded during the accretion process under the influence of hot hydrogen flows. Another hypothesis suggests that the formation of Jupiter did not begin with core accretion, but through the direct gravitational collapse of a cloud of gas and dust. Numerous similar objects formed in the protoplanetary disk, and over time, they began to merge, attracting additional matter. Convective flows in that layer, the rapid axial rotation of Jupiter generates a powerful magnetic field. That field is 20,000 times stronger than the Earth's magnetic field and creates a colossal magnetosphere. As altitude increases, metallic hydrogen gradually transitions into molecular hydrogen mixed with helium. Due to the high temperature and pressure, those gases exist as a supercritical fluid, which is a semi-liquid state. That layer has a depth of about 20,000 kilometers, and at its upper boundary begins a gaseous atmosphere spanning several thousand kilometers. The atmosphere contains 75% hydrogen, 24% helium, and 1% of other elements. Jupiter is enveloped by a dense, 70-kilometer thick cloud layer, where the average temperature is around -40 degrees Celsius. The base of the cloud cover contains water molecules, while at higher altitudes, ammonia is present, along with traces of phosphorus, sulfur, and hydrocarbons. When we observe the planet, we only see the surface clouds. They create a distinctive appearance of alternating light and dark bands parallel to the equator. That structure forms as a result of convective flows within the cloud layer. The light bands, called zones, are regions where ammonia rises as white clouds. As those clouds gradually cool down, they spread out laterally into the darker bands, known as belts. There, the cooler and denser ammonia sinks, establishing a continuous circulation. Ultraviolet light from the sun interacts with trace elements and compounds in the ammonia clouds, giving the belts their yellow-brown color. Interestingly, the zones and belts circulate the planet in opposite directions, with denser belts moving against the planet's axial rotation. Winds on Jupiter can reach speeds of up to 540 km per hour, contributing to the formation of numerous storms. A giant storm, the iconic Great Red Spot, stands out as one of the planet's most distinctive features. Located south of the equator, it extends to a depth of 500 kilometers and is comparable in size to Earth. That giant anticyclone has existed for at least 300 years, gradually changing shape and size over time. Similar storms are present in Jupiter's polar regions but are smaller, reaching depths of less than 100 kilometers. At each pole, one central cyclone is surrounded by several smaller ones, forming a hexagonal pattern at the South Pole and an octagonal arrangement at the North Pole. Cyclones and anticyclones result from the distribution of temperature variations between different parts of the planet, as the equator receives more sunlight than other regions. However, our star is not the only heat source in Jupiter's atmosphere. The planet emits more than twice as much energy into space as it receives from the Sun, a phenomenon likely due to the ongoing cooling of its interior. Jupiter has the biggest magnetosphere in the solar system after the Sun. It extends up to 3 million kilometers towards our star, while on the opposite side, its magnetotail stretches over 1 billion kilometers, reaching as far as Saturn's orbit. Jupiter's polar auroras are permanent and result from the interactions between its strong magnetic field and charged particles from the solar wind and nearby moons. A little-known fact is that Jupiter has 4 rings, which are very thin and barely noticeable. They contain dust particles created by micrometeorite collisions with its moons. Jupiter has the second highest number of moons in the solar system, with 95 currently discovered. Their sizes range from a few kilometers to hundreds of kilometers in diameter, and most have irregular shapes. They are likely gravitationally captured asteroids, particularly those with retrograde orbits. The smaller ones are simply fragments from past collisions between large asteroids. That suggests that many such objects exist that have yet to be detected. The 4 innermost satellites are relatively large and are responsible for the existence of Jupiter's rings. Beyond their orbits lie the so-called Galilean moons, first observed in 1610 by Galileo Galilei. Those moons differ significantly from the rest, as they have a spherical shape and sizes similar to that of a small planet. All 4 bear names from ancient Greek mythology: Io, Europa, Ganymede, and Callisto. They originate from leftover material after Jupiter's formation, and therefore, the Galilean moons follow elliptical prograde orbits around the planet. The first 3 satellites are in a 4-to-1 orbital resonance, meaning that for every orbit of Ganymede, Europa completes 2, and Io, 4. Gravitational interactions between those moons and Jupiter generate intense tidal forces, periodically distorting their shapes from spherical to ellipsoidal. That tidal effect is most noticeable on Io, where surface distortions reach 100 meters. Friction within the crust generates large amounts of heat, making it the most volcanically active body in the solar system. Its surface has a distinctive yellow color due to the high concentration of sulfur. Io has over 400 volcanoes, some reaching several hundred kilometers in diameter. They form massive lava flows and eject ash to a height of more than 200 kilometers. The volcanoes are a primary factor in the existence of a thin atmosphere of sulfur dioxide and other sulfur compounds. Io's surface is almost devoid of craters because its crust undergoes continuous renewal, erasing impacts over time. Another notable feature of Io is the numerous mountains, which number over 100. Their average height is around 6 kilometers, with the tallest reaching up to 17 kilometers. The mountains result from a partial overturning of crustal regions by tectonic processes. Io is also the densest satellite in the solar system. Measuring about 3,600 kilometers in diameter, it is slightly larger than our moon. Europa is the second of the Galilean moons and the smallest, with a diameter of about 3,100 kilometers. 50 kilometers deep, containing twice as much water as all of Earth's oceans combined. Europa is enveloped by an ice crust, up to 25 kilometers thick, making its surface exceptionally smooth. The few craters on the surface are no older than 90 million years, indicating that the crust is renewed periodically. That renewal process likely involves denser ice sinking and being replaced by a new layer. Europa's most distinctive feature is a vast network of cracks between 1 and 2 kilometers wide. They stretch for several thousand kilometers and form ridges that can be hundreds of meters high. Along those cracks, there are reddish-brown streaks that contain salts and sulfur compounds from the subsurface ocean. Tidal forces acting on Europa are responsible for the movement of the crust but also induce heat in its interior. Ganymede is the largest moon in the solar system, surpassing even the size of Mercury, though it has only half the mass. With a diameter of over 5,200 kilometers, above that ocean lies an icy crust, which contains rocky fragments and has a thickness of approximately 150 kilometers. On the surface, we can distinguish two types of terrain: darker areas dotted with numerous craters and predominantly lighter regions that have formed more recently. The surface also exhibits ridges and faults that probably result from tectonic activity. Ganymede has a fragile atmosphere, similar to that of Europa, and is the only moon in the solar system known to have a magnetosphere. Callisto, the outermost Galilean satellite, spans roughly 4,800 kilometers in diameter, surpassed in size only by Ganymede and Saturn's moon Titan. Callisto's surface is the most heavily cratered in the solar system, scarred by countless impacts from asteroids and comets. The abundance of craters is due to the lack of geological activity, allowing the surface to remain virtually unchanged for billions of years. Exploration of Jupiter and its moons using space probes began in the 1970s. The first to approach the planet were Pioneer 10 and Pioneer 11 in 1973 and 1974, followed by Voyager 1 and Voyager 2 in 1979. The first mission dedicated to an in-depth study of Jupiter was Galileo, which entered orbit in 1995 and collected data until 2003. Galileo included a descent probe that penetrated the atmosphere to a depth of 150 kilometers, providing unprecedented insights. The latest mission, called Juno, arrived in 2016 and established itself in a polar orbit, expected to operate until 2025. Our understanding of Jupiter remains limited, even with ongoing research and the few probes that have explored this fascinating planet. Future missions are expected to enhance our knowledge of the Jovian system and may reveal new insights into Jupiter's significance in our part of the cosmos.